Okay, so basically this is the IC, which is LM741 IC, which is a very common operational amplifier, which is sold, and you'll be using one of these in the labs. I'll talk about the pinouts in a bit, but if you open this up, if you go to the spec sheet, so just type LM741 spec sheet, then you'll see that figure I showed you, but it'll also show this is the inside of a LM741, what exactly goes in. And you can see it's a giant mess of capacitors, right? Bunch of resistors, bunch of BJTs. And just imagine wiring something like this up on a breadboard. It's like a nightmare. So you don't really wire this up. You basically just manufacture it in the right way. So all these things are put on a chip, and if the chip is this small. Okay, so now that we have that, let's go back to this. So the chip is basically at that small, size of half of my index finger, and it actually has 8 legs. Okay, the 8 legs corresponds to each leg has a number, and the way you identify what is one is through that small semicircular arc on top. Right, that tells you, so hold it in such a way that the semicircular arc is on top. The number on the left, the first leg is number 1, 2, 3, 4, and so on. Okay, so let's see what these numbers are. And once you know this, you can actually start wiring this. So I'm going to redraw this, and then we'll explain to you each what these legs mean. Okay, so we'll look specifically at LM741. Okay. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, what are these called? Well, I just write this ON and I'll abbreviate it down. ON is off, set null. Then we have P negative, P positive. Okay, and then V negative and V positive are your inputs. Then we have, okay, hold on, this slight change in sign. So I'll use this notation actually. Don't put V negative as a superscript, but put it as a subscript. Okay, V negative, V positive. And that's because I'm going to reserve the superscript for something else. So the superscript will be used now. For 4, we'll put superscript V negative. And for 7, we'll put V positive. So that's a superscript, and they have different meanings. So V negative, superscript, V positive are the supply voltages. Okay, still left with 2 pins. They are V out. So this is our output voltage. Okay, so we have one more 8. This is not connected. What NC or not connected means is that it has no meaning. It is not connected to anything. So you can ignore that. Okay, so let's try to understand this. Why do we need the 7 legs? So this particular opamp, or all opamps in general, LM741, maybe I should be more precise, actually has 2 inputs. and it has one output. And normally what we need is, usually there is an input and output. But now why do you need a supply voltage? Now, I see the LM741 is no longer a passive circuit. By a passive circuit, I mean that when you connect a LED or a bipolar junction transistor, it's basically powered by the voltage, the battery, and doesn't really need anything else to power it, right? That powers it also serves the function of providing the input and output voltage, that is the battery. In this case, the output and the input are connected to different voltage source compared to the supply voltage. So this circuit is known as an active circuit. That is, it needs an external power supply in order to run. And that external power supply has to be connected to the supply voltage. So this is external voltage. Okay, typically you supply this with plus 15 volts and minus 15 volts. So the plus 15 volts is for the positive one, V positive, and then minus 15 volts is for the negative one. So when you use this, you'll always power the op-amp with 2 power supplies. Well, you could also do it with 1 if you wire it the right way. So let's assume that you make it simple, you use 2 power supplies. One power supply will provide it with V plus. Another power supply will supply V minus. And once you have that, then you're ready to use the other 3 important ones, V minus, V positive, where V minus, V positive are with the subscript, and the V output is, depending on your wiring, you'll get a certain V out. So that is what the op-amp will be used for, summer, differentiator, and so on. And we talked about those circuits in a bit. The offset null is something which you never touch, but you might want to use it if you see that the voltage is offset by a certain value. Like say, you want it to be 0 volts, but it's actually 1 volt. So you can offset it to back to 0 using the offset null. And I don't really see a use of it because these things are usually manufactured to quite a bit of precision that you really don't need it. But just remember that those things are there. You'll never really use this. So for all practical purposes, when we talk about circuits and we draw circuits, we really don't look at any of those pins except for 2, 3, and 6. So only 2, 3, 6 for circuit diagrams. Again, I'll show you what a circuit diagram will look like. We'll show a circuit diagram like this. This is V out. This is your pin number 6. We have V with a subscript V minus and a subscript V plus. So this would be pin 2. Pin 3. Okay, the minus means that it's the negative, V negative. The plus means the positive, and then the infinity means that ideally the voltage gain, the ratio which I talked about, should be infinity. Okay, you can also show it here if you think that might be easier. You will draw it something like this. Okay. And you really we don't really bother with the V plus with the superscript, V minus the superscript, because we assume that when you're using an op-amp, you always connect those the way they're supposed to be connected. Okay, so we'll be using that diagram for all our calculations and so on. Okay, so this is what is known as an open loop op-amp. So an op-amp by nature, by the way it is shown, is open loop. By that I mean that the input and output, the output is not fed back to the input. When you close the loop, an op-amp becomes a closed loop. And the reason why you want to do that is because an open loop is unstable. So we'll never use, it's never used in this configuration. Well, there's an exception actually. Most times you won't, but there are with some exceptions. I think the comparator use it with this. Doesn't use it in the open loop configuration. Never used with some, used sometimes. So what does feedback look like? Feedback looks something like this. You take the output and take a piece of wire, connect the output to the minus. This is the feedback loop. Now, there's just two ways of doing this, right? You could take the V out, connect it to V negative, or you could take the V out and connect it to the positive. You take this and connect it to the positive. Okay, now it turns out that they are both feedback, but they're called differently, and it'll be obvious when I write it down. So this one is known as negative feedback, and this is positive feedback. And the reason why they're called positive and negative is because in one case, the V out goes to the positive. In another case, the V out goes to the negative. This is stable, and this is unstable. Okay, it's one of your homework questions is to actually do this wiring in Tinkercad and check what the output will look like. You see that it actually is unstable for positive feedback. Okay, now let's talk a little bit. We'll talk about ideal op-amps first, just like we talked about ideal diodes, where the voltage drop is close to 0. And then we'll go to the real op-amp. It's very easy, intuitive to use, and the ideal op-amp assumptions, which I'm going to talk about in just a bit. Okay, so let's look at an ideal op-amp. Okay, so let's redraw the op-amp I drew earlier. P minus, P positive, P out. Okay, now there are three things which we need to write down. One is, let's assume that there's a current going like this in. Okay, now remember that an op-amp has a very high input impedance, which is Z in is close to infinity, which means that the current has to be close to 0. So the first thing to assume is that the currents inside the op-amp to the V negative, V positive is close to 0. And that's because in ideal scenario, the input impedance is infinity. Now, in a real op-amp, that's not going to be true. There will be a very little current flowing through the input because the input impedance is not actually infinity. When you wire this in Tinkercad, you will see that the current is actually not 0. But when you do this calculation, they'll assume it to be 0. That's the first one. Okay. And then as a consequence of this, the voltage V plus is equal to V minus. Okay, so this is because V in tends to infinity. And this is because okay, I can elaborate this. Why is V plus equals V minus? Well, if you remember, I wrote down the voltage gain, delta V in, which is V. This is AV. But V in is V positive minus V minus. This is the delta V in is basically change in the voltage. So that's basically, these are the two input voltages. So it's the difference equals AV, which tends to infinity. So now we have P out equals AV, V positive, V minus. If this term goes to infinity, this we know is finite, right? The output voltage has to be finite. Otherwise, what's the use of having an op-amp? So then this term has to go to 0, right? So that infinity and 0 will give you something finite. Now, the way I've written is probably incorrect, right? Infinity times 0 is not really defined. It depends on which goes faster to, if AV goes faster to infinity, then that product will be 0. But if AV doesn't go to infinity, it's some big value, and V plus minus V minus goes to 0 faster, then it will be a finite term. So it's like two big numbers could give you something which is finite depending on the exact value. So just take this thing with a pinch of salt. Really is not what it is. Just the fact that the product will be 0. So this assumption comes from this because of this reasoning. Again, the last one really is not really used in calculations, is that Z out is close to 0. And the output impedance is 0. I'll just put it 0. Okay, which means that P out does not depend on I out. Okay, now once we have this, these are the key things we need to do our calculations with op-amps. Just these two. Okay, the voltage at the positive is same as voltage negative, and then the current inside going through the two inverting and non-inverting inputs, maybe I should have said that, is 0. So this is P minus is the inverting input, inverting because it's negative, and V positive is the non-inverting input.